Alrighty, hello everybody. This is Professor Iris Miano giving you your week 9, day 16, I believe, lecture video here on the first two sections of chapter 6. They are going to cover parallelograms all up and down, and also there's a little bit about kites as well. In chapter 6, we are introducing quadrilaterals in fine detail, and the very first quadrilateral that we need to tackle is going to be the parallelogram. That's going to be like kind of the most basic one, and you will find that a lot of the other quadrilaterals that we're going to talk about in the last section of chapter 6, section 6.3, which is in a separate lecture video, are going to be based off of parallelograms. So that's a discussion for another time. So let's get real deep into this parallelogram discussion by first defining what a parallelogram is. A parallelogram is a quadrilateral, which, if you recall, is a four-sided closed polygon in which both pairs of opposite sides are parallel. So I want to make sure that we have at our disposal notation that we could add to a figure in order to denote parallelness, the relationship of being parallel to one another on top of the figure itself. So here is a parallelogram, and I believe in your lecture notes I have a little bit of space provided for you to draw a parallelogram, and you're just doing it freehand. You're not expected to construct one, although you could if you used some of the stuff that you've learned in Construction 7, which is regarding parallel lines. You could construct a very good parallelogram if you really needed to. And so here is some notation that you could add. And it's just basically arrow points. I know there, if you look very closely on the video, it looks a little bit darker right there. That's unintentional. Really, the notation is the arrow point. The number of arrow points indicate a pair of parallel lines. So for instance, this horizontal top edge and this horizontal base edge are parallel to one another because they each have one set of arrows pointing in the same direction, whereas these two oblique lines, the other pair of lines that appear to be parallel, have two arrow points pointing in the same, upwards oblique direction. So this is one way notationally on top of a figure, a quadrilateral figure itself, you could indicate that edges are parallel and which edges are parallel to one another. Now, here is an example of something that's not a parallelogram, okay? In fact, this is called a trapezoid. If you wanted to, you could add to your notes something that's quadrilateral but not a parallelogram. And trapezoids, by definition, not that we get into trapezoids, actually trapezoids are technically not part of the curriculum here with the quadrilaterals in this chapter. But I thought I would just mention that trapezoids are a quadrilateral that has exactly one pair of parallel lines. And this one happens to be a regular trapezoid because the base angles up top and down below are congruent pairs. Anyway, that's neither here nor there. We don't need to worry about trapezoids in any kind of detail for now. We talk about them ever so briefly in chapter 10 in regard to perimeter and area. So we'll get to that a little bit later. Okay, so let's dive into some theorems. Here is the very first theorem of chapter 6, section 1. It says the diagonal of a parallelogram separates it into two congruent triangles. So if you recall, in chapter 5, that's when we first started talking about triangle congruency, and we have all of these ways to prove triangles congruent. Now here's another one involving parallelograms. So give yourself a parallelogram. Here is parallelogram A, B, D, C. I know, it's a little bit weird and feels a little out of order, the vertices configuration, but make sure that you are naming your quadrilaterals correctly. There is a rule for it. You have to go around the outer edge of vertices. You cannot go through the polygon in order to name it. So for instance, this particular parallelogram could not be named parallelogram A, B, C, D, right? That would go across, that would be going diagonally across the quadrilateral. Anyway, that's neither here nor there. So if we were to put in a diagonal BC, for instance, which I've just done so, I'm clicking forward on my PowerPoint, then you'll notice that inside of the parallelogram there are two triangles, ABC and BCD, so to speak, okay? Or, you could name them differently. There's no wrong way to name a triangle. And according to this theorem, they are congruent to one another. So there you go. Another way for us to prove triangle congruency, all you have to do is have something that's been categorized as a parallelogram, a quadrilateral, specifically that's been characterized as a parallelogram. You can draw a diagonal anytime you wish, as long as there are vertices in play, because two points determine a line. We're going to actually use that a little bit later in a proof. We're going to actually draw extra lines as we see fit, and all you have to have is 2 points to connect them. Okay, I'll show you what I mean by that a little later. Moving on to corollary 612. So corollaries are just kind of sub-theorems, always connected to a main theorem, which is that first theorem of this chapter is the main theorem, and here is a sub-theorem or corollary associated with it, and it states the opposite angles of a parallelogram are congruent. Here is a parallelogram. It's the same generic one as the previous theorem illustration. Parallelogram, you could call it ACDB if you want. Or you could start at any other vertex and go around the figure. This could also be called parallelogram CDBA, just to be clear, okay, about the naming rule. All right, so let's go ahead and look at opposite angles, okay? So we're talking about angles A and D are in opposite positions. They're not adjacent angles to one another, right? They're not vertices that are next to each other. They're opposite. They're directly across the way neighbors. They are a pair of congruent angles, and similarly but distinctly, angles B and C are also opposite, and so therefore they are congruent according to this corollary. All right, so those are the things I think you should add to your lecture notes: the arcs and, of course, the congruency statements there. Okay. Moving on, the opposite sides of a parallelogram are congruent. So again, here's your generic parallelogram. You could name it CDBA if you wanted, parallelogram CDBA. And how do we show that opposite sides of the parallelogram are congruent? We'll go ahead and put one tick mark, for example, on line segments AB and its opposite line segment CD. And you can DC, I guess is what I was calling it, BA and DC. You can name line segments in reverse, and there's no reason that it's any different than CD than I guess what I said earlier. Or, the other pair of opposite side lengths would be AC and BD. That's this congruency statement right there. Okay, so that's the consequence of this particular corollary. Moving on. Okay, and I wanted to point out a typo in the book. I believe this one is typed up in the textbook as corollary 4.1.4. Obviously, we're in chapter 6, so it should have been a 6 typo. It states the diagonals of a parallelogram bisect each other. This is a powerful one, and one that comes up quite a bit in proofwriting, I have found, in this curriculum. So go ahead and put both of the diagonals that are possible inside of this generic parallelogram ABDC. And go ahead and also note the point of intersection. I've named it E, okay? So then, once you do that, it's easy to name the line segments that come about with the intersection of these diagonals, and you're allowed to, according to this corollary, state that they are congruent pairs of line segments in the same line, right? So the diagonal AD, in being intersected with other diagonal BC, creates two line segments AE and ED, or DE rather, and those are a congruent pair of line segments. Similarly but distinctly, BC diagonal is cut in half by the other diagonal AD, and therefore creates line segments BE and CE, and they're a congruent pair of line segments, according to this corollary. Cool. All right, moving on. Two consecutive angles of a parallelogram are supplementary. All right, again, generic parallelogram. Here are all the supplementary statements that we can make. And of course, supplementary statements, or the relation of being supplementary, is symmetric. So you could easily claim that there are four more statements in which you just switch the position of the angles in the statement. So for instance, for this first one, angle B is supplementary to angle A. You could also say angle A is supplementary to angle B, and so on and so forth for all of them. So understanding the symmetric nature of this relation allows you to just, bare bones list these four relationships and understand that the reverse is also true. Okay? And what does it mean to be supplementary? Well, it means that if I was to know or not know the measures of any of these angles, I could add them together as long as they're supplementary and set them equal to 180 degrees and have a correct equation. Okay? Cool. Moving on. Two parallel lines are everywhere equidistant. So this is a little bit of a, seems like a deviation. But remember, in a parallelogram, opposite edges or sides of a parallelogram are parallel lines. And what we're saying here is that they're everywhere equidistant. So if I was to draw a line, a straight perpendicular line to lines L and M, as you see here, you could add this to your figure if you wanted to, that would be representing the distance. Remember, the shortest distance or the distance between some lines is always the perpendicular. Now, I don't have a little box, in the angle, any of the angles that are formed with the incorporation of this line, but it is indeed a perpendicular if it's the shortest distance between the two lines, okay? And if I was to try and capture this again, like figure out where the distance was between the two lines, but starting from a different point on line L or line M, it would be that same distance. If I did it over here, right, it would still be the same distance. That's supposed to be the point of this theorem, is that it doesn't matter in which way you start the measurement between the two lines, as long as you are getting the shortest distance possible between two lines that are parallel, it's always going to be the same distance away. They are everywhere equidistant. That's what that translates to. Okay? Cool. Moving on. An altitude of a parallelogram. Now, we already know what an altitude is as far as triangles are concerned. If you recall, an altitude was one such auxiliary line that was presented, and it is a straight line that starts from a vertex of a triangle, and it meets the opposite edge perpendicularly, or forming a right angle, right? So this is no different in a parallelogram. However, the altitude could be either inside of the parallelogram or outside of it. So here I want to show both the different ways that an altitude could be drawn from this particular generic parallelogram. Okay, so here's probably the most intuitive way to draw an altitude from vertex A, let's say, and drawing an altitude from vertex A happens to have the altitude completely inside of the polygon, which, if you recall how they were presented for triangles, that seems reasonable, right? Now, we could also, though, draw the altitude, if we wanted to draw it from vertex C, it would be existing outside of the parallelogram, and that's perfectly fine. It's still an altitude. It's meeting either the opposite edge or an extension of the opposite edge perpendicularly, so forming a right angle, as you can see with these little boxes here. Okay, so hopefully that illustrates the two different ways you could see an altitude inside of a parallelogram. It could either be inside of the polygon or outside of the polygon, meeting an extension of the opposite edge. Okay, this extension being represented with this dashed blue line. Cool. All right. Moving on. Remember, anytime I'm talking about something in a lecture video that's unclear, you want some more clarification, it's a good idea to maybe in your lecture notes jot these questions down, and then when we come back to class to discuss these sections, it could be good a time for you to ask those questions. And remember, you don't have to ask them verbally. If you have anxiety about talking in front of the entire class, by all means, direct message me in the Zoom meeting so that we can address it in an anonymous way. Anyway, back to the material. Here's the 8th theorem in this first section here. Quite a lot of theorems in this in this one. It states that in a parallelogram with unequal pairs of consecutive angles, the longer diagonal lies opposite the obtuse angle. Okay, so a lot of words going on here. What is it actually saying? Let's go ahead and give ourselves generic parallelogram ABDC again. I have both of the diagonals drawn with the intersection point E presented. Okay, so which diagonal is longer according to this theorem? Well, you could probably, from inspection, determine that BC is longer than AD, right? I mean, maybe it's terribly obvious, but this theorem is making it clear which one is the winner by virtue of which diagonal is opposite the obtuse angle. So the obtuse angle in the parallelogram, okay, would be angles A and D. Now, since there's extra edges going on in vertex A, besides the outer edge of the parallelogram, it's probably best to use the 3-letter code for the name of the angle. So what I'm saying is, in regard to the parallelogram, the outer edge polygon, angle BAC and angle CDB are the obtuse angles in the parallelogram, so therefore them being opposite diagonal BC, that fact makes BC the longer of the two diagonals. Again, it might just be terribly obvious from looking at the parallelogram and its diagonals which one is longer, but you could use this theorem to justify for sure that you know which one's longer. It's always going to be the diagonal that's opposite the obtuse angle in the parallelogram. Okay, talk that one to death. Let's move on. Oh, sorry. So yeah, I have this statement that I want to, I guess, encourage you to write on your lecture notes, that BC, the length of line segment BC is greater than the length of line segment AD. Okay, cool. Moving on. Let's go ahead and write a formal proof of a theorem. So let's start from the very beginning. And the only thing that we're given here is the theorem. The opposite sides of the parallelogram are congruent. Okay, so we need a parallelogram to start with, I would think. So that's where I'm going to start the process of writing the formal proof, is to come up with a drawing. So give yourself a quadrilateral, give it some vertex names, right? Name the places where the edges meet, the points that are the vertices, and call it a parallelogram. Like, in calling it a parallelogram has some power, right? Like, there's details associated with the definition, and there's also details associated with some of the theorems that have been presented in this section that have already been proven in the book and we can use right away. So, but we want to prove that the opposite sides are congruent. That's the thing that we're trying to prove here. So that'll be specific to the drawing that I make. So the given statement will be that I have a parallelogram, and the thing I'm trying to prove is that the opposite edges of that specific parallelogram that's drawn are going to be congruent to each other. So I'm going to have two congruency statements associated with my proof statement. And here is all of that. Here's a parallelogram ABDC, or quadrilateral ABDC is a parallelogram. That's going to be my given statement. Okay, and this right here, this just rectangle symbol in front of the vertices that name this quadrilateral, this is just mathematical shorthand for quadrilateral. Okay, like how when we name a triangle, we put a little triangle symbol in front of the 3 letters that name the triangle, and it's read as triangle ABC or whatever the vertices are. This is read as, the given statement is quadrilateral ABDC is a parallelogram. Okay, and then our proof statement will be that AC is congruent to BD and that AB is congruent to CD. Okay, those are the opposite edges that we need to show are congruent. That's the thing we're trying to prove. Okay, so let's put this all together in a statements and reasons chart style proof, table, if you will. And always the first statement is whatever's given, and you say it's given. That's your freebie, right? Okay. Moving on, I go ahead and draw a diagonal, CB. Now you could draw the diagonal AD if you want to. Drawing this particular diagonal was a stylistic choice. And drawing a diagonal as the first step in this particular proof is something that's not necessarily intuitive. I mean, did you guys know that you can add lines to your figures as long as there are vertices? Well, now you do. And here's an instance in which I see it as being very useful to coming up with this proof, because if I draw a diagonal, I can use that very early theorem that was presented in this section that said that a diagonal in a parallelogram cuts the parallelogram into two congruent triangles. So I'm about to make the two triangles that result with the incorporation of this diagonal congruent, and then I'm going to CPCTC hey my way into making the proof statement happen. So spoiler alert, that's my thought process that I'm going through. And so anytime you want to draw a diagonal, or you want to just take two vertices, points, whatever they're being categorized as, and you want to connect them with a line, you can do so. And it's using a very early postulate. I want to say it was postulate 1, right? The very first postulate, which was, it's being paraphrased here as 2 points determine a line. But I think the actual wording was closer to, in a plane, there is only one line that exists between 2 points, right? And so that's an interpretation of that is to say that 2 points determine a line, and the usefulness of it, as I see it, is being able to join together any vertices within a figure as you see fit for your proof writing. So here we go. I have a diagonal drawn, and this allows me to make the claim that the two triangles that are formed with the incorporation of this diagonal are indeed congruent triangles, and I'm using that that theorem that was presented earlier in this section. Okay, so now that the triangles are congruent, I can say that any corresponding parts of those congruent triangles are congruent. That's CPCTC. So I'm going to go ahead and make my proof statement happen, and the justification is simply that 5-letter acronym, bunch of C's, a P, and a T, but in a particular order. CPCTC, hey. So hopefully you've come up with either your own, or you use that conga line kind of jam in order to remember in what order those letters come. Okay, and again, just as a reminder, what does CPCTC stand for? It stands for corresponding parts of congruent triangles are congruent, okay? And that's what I get to say here. In the previous statement to my fourth prove statement, right, I said that the two triangles formed with the incorporation of the diagonal are congruent to each other. So any corresponding parts of those two congruent triangles, I get to say are congruent. And that just so happens to be the edges that are opposite in the parallelogram. So that makes my prove statement happen for me, and that allows me to prove the theorem in question. And that's a wrap. Relatively short proof. You're going to find that as we move forward in this class, the further we go, it seems like the shorter and shorter our proofs become, because the things that we have in our basket to draw from, our definitions, postulates, and theorems, they can go further. The farther we go into the curriculum in this class, right? We just have more and more powerful theorems at our disposal. Okay, so hopefully that's a feeling that you guys are having with your proofreading. Okay, moving on. I believe we are now getting into the second section. So we're like halfway-ish done with this lecture video. I think the second half, parallelogram and kite section, go a little bit quicker, but you be the judge. So let's go ahead and read this first theorem in the next section, section 6.2, and it reads, if two sides of a quadrilateral are both congruent and parallel, then the quadrilateral is a parallelogram. Cool. So this probably sounds a bit familiar, right? But I want you to look carefully at the wording, because what's being stated here is that you have to have some specific elements in play, and then you can prove, using this theorem, right, that a certain quadrilateral is a parallelogram. So even though the generic figure that we're working with here in illustrating this theorem, like it clearly looks like a parallelogram, it cannot be assumed to be so unless the hypothesis information has been established. And by the hypothesis information, I mean both two sides of the quadrilateral both congruent. So here's them being congruent, and I'm choosing line segments A, B, and DC in this illustration, but I could have easily also illustrated this with the other opposite sides of the quadrilateral AD and BC. Okay, but for the purposes of just illustrating this theorem, I've chosen A, B, and DC. Here they are being, if I can show that they're congruent, and if I could show that they're parallel. So notice this new notation that's being thrown in the mix. And yes, I have a parallel statement off to the side here. If these two things are in play for a quadrilateral, then I can claim that the quadrilateral is indeed a parallelogram. Okay, so it's a little bit of a converse situation, excuse me, compared to related theorems that were presented in 6.1, just to be clear. Okay, great. More. Let's show another way that we can prove that a quadrilateral is a parallelogram. So give yourself generic quadrilateral at this point. Not sure if it's a parallelogram. What do we need to establish before we can prove that it's a parallelogram? Well, if you're going to use this theorem, you have to establish that we have opposite sides are congruent for both pairs of opposite sides. If you can show that much, then that's enough to say quadrilateral ABCD, in this case, is a parallelogram. Okay? Notice that I transposed the position of the names of the vertices so that going around in a clockwise fashion starting at A has it reading as ABCD. That is distinct from what I did in 6.1 for no particular reason, just stylistic choice, I guess. All right, cool. What's another way that we can prove that a quadrilateral is a parallelogram? What would we have to establish first? Well, if you're thinking about using this third theorem in section 6.2, it would be throwing in the quadrilateral's diagonals, and if they bisect one another, so if you can establish that the diagonals, as they cross each other, cut each themselves into congruent pairs of line segments, then that's another way you can prove that the main figure, the outer edge polygon quadrilateral, is indeed a parallelogram. Okay, cool. Whew. All right, so that's a bunch of parallelogram stuff. We're going to put a pin in that for now and introduce a kite, which is another type of quadrilateral. It's a special type of quadrilateral. It's very distinct from the parallelogram in that it has, by definition, two distinct pairs of congruent adjacent sides. Okay, whereas the congruent sides in a parallelogram were opposite sides. If they're adjacent to each other, then you have a kite. So here is kite WXYZ. That's one way that you could name it. And here is one pair of congruent adjacent sides, XW and ZW. And then here is a distinct congruent pair of sides, XY and ZY. Okay? And you may notice something else about kites, and it comes in the form of a theorem that comes later on. But yeah, so if you can establish these two items here, and notice that they're adjacent pairs of congruent edges, then you can categorize a quadrilateral as a kite, by definition. Okay? And then there's a theorem that we have associated with kites. So this is a consequence that is not associated with the definition, but it is associated with kites by theorem, and it's that a pair of opposite angles are congruent. Now, which pair of opposite angles are congruent? Is it W and Y, or is it X and Z? Well, it turns out it's X and Z in this particular figure, and the way that you know that you have the pair of opposite angles that are congruent is that it is the angles that link together the non-congruent edges. So right, edge XW and XY are clearly not congruent to each other. So that means the vertex X that joins those non-congruent edges together must be one of the pair of congruent angles. Similarly, notice that ZW and ZY are non-congruent edges, and so that means that the vertex that holds them together, Z, must be the other side of the congruent pair of angles inside of this kite. Okay, so that's the rule of thumb. So the theorem states that we have one pair of opposite angles that are congruent in a kite. For this particular kite, it's angles x and z are congruent. And the way that you know that they're the congruent pair is that they're the vertices that link together the non-congruent edges. Okay, that's how you can tell. Moving on, next theorem. The line segment that joins the midpoints of two sides of a triangle is parallel to the third side and has a length equal to that, to 1/2 the length of the third side. That was kind of a word salad, right? Like, what is that even saying? I definitely think that we should illustrate this theorem with a figure. So enter generic triangle ABC. Let's take a line segment that joins the midpoints of two of the sides, like so, okay? So I believe you have space and maybe even a triangle that's already in the lecture notes. And so definitely draw yourself midpoints D and E on line segments A, B, and AC respectively, and then join them together with a line, okay? Then you can state that these lines are parallel to one another, and that the line segment inside the joining of the two midpoints, DE, is exactly half of its parallel counterpart edge, which is the base in this particular illustration. So hopefully this figure does a heightened, like an extra good job of being able to illustrate what's being said in this theorem, because just reading the theorem alone, personally, I'm like, I'm a little bogged down by like the use of so many terms all at once. I don't know. Personally, it's just a lot. I call it a word salad, whenever a theorem is just like too much for my brain to handle. And I always go for drawing a corresponding figure whenever I can to like just kind of put down all of the ideas in something a little bit more visual. So hopefully that was helpful. Okay, now let's use this theorem in order to tackle this exercise. It's a little bit of a three-parter. Please note that this figure is not drawn to scale at all. So we're just going to take the, the measurements at face value and use what was just presented, I'll go back one, in this theorem in order to determine the length of the edges in the parts A, B, and C that they want us to calculate. Okay, now remember, if they're joining midpoints, if an edge is joining midpoints and it's parallel, and that means it's parallel to the edge that it's not touching, and it's half the length of that parallel edge. So let's take that into account. Okay, so notice that X, Y, and Z are midpoints of the sides of triangle RST. So specifically, X is the midpoint of RS, Z is the midpoint of RT, and Y is the midpoint of ST. Okay, so we have this like inner triangle that has edges marked as far as their length are concerned. So X, Z is the midpoints connected here and here, right? And so you can tell, hopefully, that XZ is parallel to ST, right? Hopefully that's pretty clear. Furthermore, ZY, the connection of those two midpoints, is parallel to RS. So there's going to be a relationship between ZY and RS is one of the things we were asked to find the length of. ST as well for part B. And then finally, the link between midpoints X and Y, is this length 6 edge, is parallel to and has a relationship with line segment RT, and that's the one in part C. So what's the relationship? Well, the inner edges that are the connections of the midpoints are half the measure of their parallel counterparts on the outer edge. So therefore RS, which is parallel to ZY, has to have what length? Well, ZY is 8, so RS must be double that. That's 16, okay? ST, this like bottom edge here, is parallel to the connection of midpoints that is length 10, double the 10, and you'll get ST. That's what makes ST length 20. And lastly, RT is parallel to the midpoint connection line segment XY, which has a length of 6. So that means RT must be double that, makes it 12. Okay, cool. So that's the relationship. If you have two, in a triangle, if you have two midpoints connected together, that edge that you create is going to be parallel to the edge that you haven't touched yet, and it's going to be exactly half the length. Okay, cool. Let's go ahead and have, I think this is the last example, maybe, I can't remember, we'll see, in which we're going to tackle a proof together. And it's going to be a parallelogram proof. So we have a quadrilateral WXYZ that right off the bat is being categorized as a parallelogram. And it has diagonals WY and XZ that appear to be intersecting at point M. Now notice that the categorization of M being the intersection of the diagonals is not explicitly stated in the given statement, but it's clearly marked in the given figure. So that makes it also part of the given statement. Hopefully that's clear for everybody. And we want to use the figure and the given statement and reason our way through to being able to state the triangle WMX, which is what? WMX. That's this kind of upper interior triangle, is congruent to this lower interior triangle YMZ. Okay? Seems legit, but how do we get there? Let's see. Okay. So here is the setup, statement and reasons chart style thing. I went ahead and just fed the given information into the first statement and said it's given. That's always what you do to start off with. Nothing has ever changed or will ever change with these chart style proofs. Always that's your first move. Now, it seems to me like, if I know that this is a parallelogram and these are diagonals, I can say something about the line segments that are formed with the intersection of these diagonals, right? And that's going to go a long way in proving that these two triangles are congruent to each other. It's like two pairs of sides of the triangles themselves get to be connected as congruent pairs, right? Because diagonals of a parallelogram bisect each other. That's that was actually presented as a theorem in 6.1, right? The very first section that was presented here. And since we're in 6.2 writing up this proof, definitely anything from 6.1 is fair game to be used in proof writing, okay? So that gives us two sides for each of the triangles. Now, there are a couple of options for moving forward and being able to say that these two triangles, the upper interior triangle and the lower interior triangle, those are the two we're trying to say are congruent. Where do you think we should go with it next? All right, I see two separate options here. And they are, here's the one that I have prepared in the PowerPoint, and then we can discuss the other one as well. So I'm going to go ahead and say that the opposite edges of parallelogram are congruent, which happens to be, I could say that in addition to WX and ZY being congruent, I can also say WZ and XY are congruent, another congruent pair of edges. But that doesn't get me where, I need to go with proving that these triangles are congruent to each other. And then from there, I can side my way into saying that the two triangles are congruent. Alternatively, at statement 3, I could have also said that angle WMX is congruent to angle YMZ because vertical angles are congruent, and then sided my way into the triangle congruency statement, which is the proof statement. So that's another way that this proof could be written. But I chose this way. Why? It was the first way that I thought of when I was writing it, and so that's what makes it the best way. Like the first way you think of doing something when there are multiple ways to do it is going to be the most intuitive way, probably, right? And that's what makes it the best way, because I know people are going to ask, well, which one's right? Which one's more right? Which one's like the best way? neither. They're both really good methods, and they both happen to use the same number of statements. Not that it's a competition ever in trying to like make your proofs as concise as possible. I mean, I guess it is kind of a good feature of a proof if it is concise, because who wants to read a lengthy proof that's unnecessarily long? Sure. But you know, they happen to, both of the methods that I describe are just as lengthy as the other, and they both end up getting to the proof statement, justifiably so. And that's always your goal in your proof writing, is to start with the given information, which includes the figure, reason your way down to the proof statement, justify every step along the way. That is proof writing. If you can do that, then you have garnered yourself an incredible skill, and it's really like the main thing that you want to take away from this class in general. Okay, great. So that's, I believe, all the stuff that I've got for you in these first two sections of Chapter 6. Have fun with it. Here's some homework problems I suggest that you tackle. If you have any questions about this lecture video or the homework problems, that's what we'll be talking about on, day 16. I don't want to say the date of it in case I reuse this video, but I believe it's day 16 of week 9 or some such thing. Cool. See you in class very soon. Take it easy. Thanks so much for your attention.